Okay, we are recording and we are continuing our discussion of section 12.7, triple integrals. And you saw in section 12.5 some applications of double integrals, and all the applications of double integrals in section 12.5 can be extended to triple integrals. A good example, if the density function of a solid object, now not a lamina, the density function of a solid object occupies a region and has a variable density function given by rho of x, y, z, and it's in units of mass per unit volume. Then the mass is given by this formula. So this is just an extension of the mass formula, the total mass formula that you learned in section 12.5, right? It's just an extension of the total mass formula. The moments also, the definitions are similar to what you learned in section 12.5. But now, of course, since we're dealing in three-dimensional space, we don't have, like, you know, when you have the XY plane, you have moments about the axes. But in three-dimensional space, you have moments about the coordinate planes, okay, because you have X distances and Y distances and Z distances. And those distances are based on the plane. So, for instance, if the moment about the YZ plane, well, you're interested in how far a point is from the YZ plane, that's an X distance. So that's why we insert the X before the density. And for the moment about the XY plane, a point that's a certain distance from the XY plane, that would be a Z distance. So, you know, that's why you have Z there. And then, you know, the MXZ moment is defined there. The center of mass works just like section 12.5. It's just you have three. Now the center of mass, or the centroid, is, well, I guess here they say if the density is constant, the center of mass of the solid is called the centroid. Okay, so center of mass is a general term. When you have constant density, the center of mass is a centroid. Okay, all right, so let's see here. Now, just to mention, they talk about also moments of inertia. And we won't get into moments of inertia in this class, but you know, there's the definitions, and also another definition is electric charge, the total electric charge on a solid object occupying a region E and having a charge density. So this is, you had a charge on a lamina, right, back in section 12.5. Let me just see here. That was example 1, finding charge by integrating charge density. Example 1, section 12.5, you had the charge distributed over a triangular region. Well, now we're having total electric charge distributed over a solid E. And incidentally, another application, we won't get to it, but you can have probability functions. You can have probabilities, and you know, again, there's a class in your senior year. Probably you would take it if you wanted to in your senior year, maybe your junior year. You would need this class. You need this class to do it, but it's mathematical statistics. Okay, and there's different levels of mathematical statistics. You know, like you have calculus 1 and 2. Well, mathematical statistics, normally you have mathematical statistics 1 and 2. You know, and then you can even go more advanced than that. But at any rate, let's go ahead and get to an example where we're going to find center of mass. So let me go ahead and Okay, so let you copy this example down. So it says we're finding the centroid, and again, that's because we have constant density. All right, let you copy the example down, and then we'll work it out. This example that we're working out is actually the same as example 5 in the textbook, but we'll work it out here. Okay. Okay, so in this problem, we want to find the centroid of a solid that is bounded by a parabolic cylinder in the planes x equals z, z equals 0, and x equals 1. Assume constant density. Now, I'll mention for your problems in the homework, obviously, if the solids are too complicated, the problems become very hard to do because you need to have an idea of what the solid looks like in order to find the limits, right? So of course we have to get an idea of what this solid looks like before we can find this centroid. So all right. So you have. Let me ask you this: does the cylinder x equals y squared, does it bound the solid on the sides or on like, well, what I'm trying to say is this. Let's start like this. Let's start like this. Hold on. The planes z equals x and z equals 0. Okay, so the plane z equals 0. What plane is that? That's right. That's the xy plane. That's right, Norina. And this is going to be the bottom of the surface, or bottom of the solid E. The plane z equals x is going to be the top of the solid E. So functions where you have z as a function of x and y are bounding surfaces on the top and the bottom of the solid. Okay. Now, but a solid can't just be bounded on the top and the bottom. It also has to be bounded on the sides. Well, x equals y squared, that's a side boundary. That's a side boundary of solid E. Think of the parabola y equals x equals y squared, and then raising that up and down. That'll form a curtain that goes up and down. And x equals 1 is another side boundary of the solid E. So if we put this information together, okay, this is what we're going to get for our solid. Right, this is what we're going to get. Kind of looks like the front of a vacuum cleaner. Let me give you a moment to copy the figure down, and then we'll talk about the limits here for our total mass. Please let me know if you have any questions. Okay, so the dz part, oops, dz goes from the bottom surface to the top surface. The bottom surface is at z equals 0. And then the top surface is the z equals x. So x on top means z equals x. So those are the z limits. Now what you do is you project this solid E. I mean, this is your solid, right? What plane does the solid get projected into if you are integrating with respect to z first? What plane does the solid get projected into? The xy plane, the yz plane, or the xz plane? What do you think? So to determine our region D, okay, we have to determine always mess that up. We have to determine our region D. Because now we got to do dx dy. That's section 12.3. So we would project the solid into the xy plane. So projecting the solid into the xy plane gives you this here. This is your solid. And this is your region D. I will redraw it here. This is your region D. Now let me just see one thing here. No, I didn't draw that right. I didn't draw that right. Nope. Nope. I'll have to erase. I'll just have to erase this. Hold on. Let me see. Wait, I know what to do. I know what to do. Oh, I know what to do, class. Hey, how about that, huh? There's no stopping Dr. Duty now. Now that he knows what to do there. So I'm trying to be very, I have my problem solving hat on, and I'm trying to, work through the problem like as a student would. And in other words, what I'm trying to say is I'm not like staring at my notes and just telling you what to do. I'm not staring at my notes. I'm adding things to my notes, and that I hope will be helpful for you to help you learn how to think about this. So let's draw that X and Y axis again. And this is the region D. That's this here. That's the region D. So this is clearly 1. You have a function on the left, x equals y squared, and you have a function on the right, x equals 1. So there are your x limits. And then y goes from -1 to 1, right? So there are your y limits. And now you can just compute the mass. So, of course, I'm going to want to see work on your next exam. I'm going to want to see your integration work, just like you did on the 3rd exam. So now I'm going to iterate the density. Remember, this density here is constant. We were given constant density. And so you do the inner integral. All right, you're going to get here. Now, let me know when you're ready to move to the next page. Ashfia, how are you feeling with this? Are you comfortable?
Good.
Christy is good. All right, good. And what about Ashfia? All right, Arian, how are you dealing with it? You're good. All right, wonderful, wonderful. Arian, how about you? Good, good. Okay. Okay, so now let's just keep going with this. I trust everybody has it okay. Let me know if. So I'm working it out here, just like I have to model. what to do here. And now the next integral, now it's a section 12.3 problem. We got integrate with respect to x and then y. So hopefully all the steps here are pretty straightforward. I'll give you a moment to copy it down. In the end, for the total mass, you're going to get 4 rho divided by 5. Now we don't know what rho is, but it's not going to matter. It's not going to matter in the end. But at least you see how to, doing a triple integral, it's really no different than doing a double integral. It's just you have an extra integral to worry about. And now that we have the total mass, what's nice is, of course, now we need to find, the moment about the, we need to find the moment about the xy plane, the moment about the yz plane, and the moment about the xc plane. If we go back to the picture, here, and I'm going to just take this off now. So remember, our solid E has constant density, and we want the balance point. We want the balance point for that solid E of constant density. So we need to find an x bar, a y bar, and a z bar. And of course, as you know, x bar is the moment about the yz plane divided by the total mass. Y bar is the moment about the xz plane divided by the total mass. And z bar is the moment about the xy plane divided by the total mass. But given the orientation of this solid E, one of these centroids we can get without any work at all. We know, based on looking at the solid and how the symmetry of the solid E here, this front end of the vacuum cleaner, there is one coordinate that we can get without any work at all. It's either x bar, y bar, or z bar. So, okay, Norina, you're right, the y bar. Because if you notice here, hold on, along the x-axis, or I should say, if you think of not the x-axis, if you think of the xy plane, and I guess maybe I can try to do a little, I knew I would mess this up. I'm going to clear this. Okay, so you see how the XY plane cuts the solid in half. It splits it. It splits it basically right down the line. You know what I mean? It splits it. So this means then that Y bar of our centroid has to equal 0. There's no work involved in getting that. But of course, the solid is not, it's not balanced. So in other words, this solid is balanced with respect to the XZ plane. With respect to the XZ plane, the solid is balanced perfectly. There's an equal amount of mass to the right and the left of the XZ plane. And distance-wise, the mass is equally distributed about the XZ plane. But the mass is not equally distributed with respect to the XY plane or the YZ plane. So X bar we have to compute. That means we have to find the moment about the YZ plane and divide by the mass that we just found. And then Y bar would be the moment about the XZ plane. Hold on. No, Z bar. Z bar would be the moment about the XY plane divided by the mass. Right. So some of these problems that you're going to encounter in the homework, some of these problems, and even on your next exam, sometimes you can save a little time by just looking at the symmetry of your figure. So okay, we established that that the total mass is equal to 4 rho divided by 5. 4 times the constant density divided by 5. Now, I'm not showing all the other steps. Like you would of course need to show all the other work on your exam. But in the interest of time, I mean, I think you can do the rest of this. So, all right, the moment about the XZ plane is equal to 0. We already talked about that. The moment about the YZ plane, so now the integrand is x times the density. But notice that the limits don't change. I mean, we're doing dz, dx, dy, and all of the limits stay the same. Once you compute the limits, you're done. You don't need to recompute those. You just have to do this new integral, and you can work it out, and you'll get 4 times the density divided by 7. The book in example 5 shows you it details some work for you. So for this, and the moment about the YZ plane can be shown to be 2 times the density over 7. So I'm sorry I don't have enough time to go through those calculations with you. I mean, what I'm trying to say is, I think you can do those calculations without any problem. So I'm not worried. And I'd like to, if I can, I maybe try to give you a little more classwork time. But see example 5. Example 5 in section 12.7 for more details. Now all that's left is now we can find the centroid. And we already know that y bar equals 0. And we already know that. Okay, so let me just ask you something here on this problem. So we agree that y bar equals 0. And would x bar, do you think I mean, if we want to be careful how I phrase it. So like, here's a half. Would x bar be greater than a half, or would x bar, you think, be less than a half? In other words, what I'm asking is, given the shape of this solid E, is it, and this halfway mark, is the solid E with this constant density heavier from 1 to a half, or is it heavier from a half to 0? What do you think? In terms of mass, is it heavier? So like, think of taking the mass, think of taking the solid and splitting it hold on here, along this halfway point. Is it heavier from 1 to a half, or from 0 to a half? What do you think? So this is kind of like, you ever pick up a box, or you ever buy something at the store, like I don't know, a microwave oven or a TV or something, and you notice, hey, and you try to lift it, and you almost fall over because it's heavier on one side than the other side. You ever have that kind of experience where it's like, okay, I got to turn the box around so that the weight's closer to my body? You ever have that experience where the weight is not, that the mass is not really distributed equally for the object in the box? Has anybody had that experience? Yeah. So, all right, and Narina, you're right. X bar is going to be is going to have to be greater than a half. That's right, Lexi. Because this mass, with respect to the x-axis, it's top heavy as you go. It gets heavier and heavier as you move away from the origin. The mass gets heavier and heavier, moving in the direction of the x-axis. So x bar, whatever it is going to have to be greater than a half. Going to have to be greater than a half. So, you know, we can sort of think sensibly about if our answers are reasonable. And so, of course, to compute the center of mass, I guess it's the centroid, technically, right? This is the centroid, technically. But center of mass is fine. But when we take the moment about the YZ plane and divide by the total mass to get X bar, we have this here. And 4 rho over 7 divided by 4 rho over 5. And you know how to divide two fractions. 4 rho over 7 times the reciprocal of 5 over 4 rho. Let me just make this a little nicer. Right. So the rows are going to simplify out. Going to make this look good. There's a row. There's a row. So the rows simplify out, and you get 5/7. And 5/7 is greater than a half, as it should be. And the Z bar turns out to be 5/14. 5/14 is less than a half. So this means with respect to if you think about from above the XY plane from 0 to 1, if you were to look at the mass, how it's distributed, there's more mass below the halfway point in the direction of the z-axis than above the z equals a half plane. So there you go. There you go. And then hopefully it's reasonable based on the picture. How many think this is really absolutely fascinating? I mean, you think this is important for aeronautical engineering, center of mass? Absolutely it is. It is. That's right. Narina knows. Alexander knows. Yeva says for telescopes like the Webb telescope. Sure. All right. Are there any questions on this example before I stop the recording? Okay, very good. Very good. All right. Excellent. So we're done now with section 12.7. Excellent.